Hi, chemistry students. Welcome to this lesson on 10.3, where we'll find and focus on the percent composition of a compound. You'll notice this week that you have a little bit of a murder mystery lab. I hope you guys enjoy doing that. As usual, as you guys are working through these problems and your discussion problems, please let me know if you have any questions. I use your discussion for you guys to kind of work on those problems together. So please make sure that you're understanding how to do those problems so that when you get to the test, you'll understand how to do these as well. But as usual, let me know if you have any questions. So the relative amounts of the elements in a compound are expressed as the percent composition or the percent by mass of each element in the compound. The percent composition of potassium chromate, for example, is potassium, 40.3%, chromium, 26.8%, and oxygen, 32.9%. But how can we find those percents? That's what we're going to focus on. These percents must always total 100%. And if we add them up, the 40.3, 26.8, and 32.9, we will get to 100%. So that's very important to remember as well. The percent composition of a compound is always the same. So that is always also another thing to remember, that the percent composition of a compound will always be the same, and the percents must always total 100%. Percent composition from mass data. If you know the relative masses of each element in a compound, you can then calculate the percent composition of the compound, and that's what we'll do now. The percent composition from mass data, the percent by mass of an element in a compound, will be the number of grams of the element divided by the mass in grams of the compound, and then multiplied by 100. So to get the percent by mass of an element, we take the mass of the element, divide it by the mass of the compound, and multiply it by 100 to get the percentage by mass of the element. So let's go through a sample problem where we will calculate percent composition from mass data. When a 13.6 gram sample of a compound containing only magnesium and oxygen is decomposed, 5.4 grams of oxygen is obtained. What is the percent composition of this compound? Let's list our knowns and unknowns. The percent by mass of an element in a compound will be the mass of that element divided by the mass of the compound multiplied by 100%. We know the mass of the compound is 13.6 grams, and the mass of oxygen is 5.4 grams of oxygen. The mass of magnesium will then be just 13.6 minus 5.4. So we know that we have 8.2 grams of magnesium. The unknowns that we need to find are the percent by mass of magnesium and the percent by mass of oxygen. And let me see, it's kind of cut off there. And yeah, let me just move this up just a little bit so we can see it a little better. Perfect. So unknown, we want to find the percent by mass of magnesium and the percent by mass of oxygen. So let's solve for the unknown. We'll determine the percent by mass of magnesium in the compound. So the percent magnesium will equal the mass of magnesium divided by the mass of the compound multiplied by 100. The percent magnesium equals 8.2 grams, which we got from subtracting the total minus the grams of oxygen, dividing by the mass of the compound, which they gave us was 13.6 times 100. So we get the percent magnesium after exiting out the grams. We get percent magnesium is 16.29% magnesium. Determine the percent by mass of oxygen. That the percent oxygen will be the mass of oxygen divided by the mass of the compound times 100. We know that the mass of oxygen is 5.4 grams divided by 13.6 mass of the compound times 100. Grams cancel out and we get percent oxygen is 39.71% oxygen. Does the result make sense? The percents of the elements do add up to be 100%. So we do know that we are probably right. You can also calculate the percent composition of a compound using its chemical formula. The subscripts in the formula are used to calculate the mass of each element in a mole of that compound. And using the individual masses of the elements and the molar mass, you can calculate the percent by mass of each element. So the percent by mass of each element will be the mass of the element in 1 mole of the compound divided by the molar mass of the compound multiplied by 100%. So we'll look at this sample problem now. Calculating the percent composition from a formula. Propane is C3H8, so 3 carbons, 8 hydrogens. This is the fuel commonly used in gas grills, is one of the compounds obtained from petroleum. Calculate the percent composition of propane. So let's list the knowns and unknowns. We will calculate the percent by mass of each element by dividing the mass of that element in 1 mole of the compound by the molar mass of the compound and then multiplying it by 100%. We have a couple of knowns here with a mass of carbon in 1 mole of C3H3 will be 3 moles because we have 3 carbons times 12.01 grams per mole because 12.01 is the mass of a carbon, 1 carbon atom, and that will equal 36.03 grams per mole. The mass of hydrogen in 1 mole will be 8 because we have 8 hydrogens in propane times its molar mass taken from the periodic table to equal 8.064 grams per mole. So the molar mass of propane will be 36.003 grams per mole plus our hydrogens, 8.064 grams per mole, to be the total mass of that compound is 44.09 grams per mole. The unknowns that we're trying to find is the percent by mass of carbon and the percent by mass of hydrogen. So the percent by mass of carbon, we will take the mass of carbon in 1 mole, divide it by the molar mass of propane and multiply by 100. So we took 36.03 because that was about 12 times 3 divided by the whole mass of the compound times 100. And the percent by mass of carbon in propane will be about 81.72% carbon. And that makes sense because carbons are they have more mass than a hydrogen. Each of these carbons has 12 grams per mole, and each of the hydrogens only has 1. So it makes sense that carbon will take up the majority of that mass of the compound. Let's figure out hydrogen then. We take the mass of hydrogen in 1 mole, which is about 8.064, dividing by the molar mass of propane, and we get 18.29% hydrogen in that compound. And that's how we can determine the molar mass percentages from a compound and a molecular formula. The percents of the elements do add up to 100 when the answers are expressed in 2 significant figures. So I think we're on a good way. I think we got it right. The percent composition then as a conversion factor, you can use percent composition to calculate the number of grams of any element in a specific mass of a compound. And to do this, you'll multiply the mass of the compound by a conversion factor based on the percent composition of the element in the compound. Percent composition as a conversion factor. So propane is 81.8% carbon and 18% hydrogen. We just figured that out from our last practice problem. You can use the following conversion factors to solve for the mass of carbon or hydrogen contained then in a specific amount of propane. So these conversion factors, 81.8 grams of carbon for 100 grams of propane and 18 grams of hydrogen for 100 grams of propane. So let's use those conversion factors to then calculate the mass of an element in a compound using the percent composition. Calculate the mass of carbon and the mass of hydrogen in 82 grams of propane. So we'll list our knowns and unknowns. We'll use the conversion factors based on the percent composition of propane to make the following conversions: grams of propane into grams of carbon and grams of propane, and then grams of hydrogen. The knowns are, they give us a mass of propane of 82.0 grams. And the unknowns are, we want to find the mass of carbon in that sample of 82 grams and the mass of hydrogen in that sample of propane of 82 grams. So we're going to use our conversion factors to calculate the mass of carbon. We'll first write the conversion factor to convert from the mass of propane to the mass of carbon. So we know because in 1 mole of propane, we had 81% carbon, we can then make a conversion factor where that there will be 81.72 grams of carbon for 100 grams of propane. That's from our previous sample problem. So using that conversion factor, we'll multiply the mass of propane that they give us by the conversion factor, and we'll cross out grams of propane to get a final 67.1 grams of carbon. So that is how much grams of carbon are in this gram sample of propane. And that makes sense. There's 81.82, percent of this sample will be carbon. And then to do hydrogen, we'll use the hydrogen conversion factor, which was 18.29% from the given problem. So we know that 18.29 grams of hydrogen will be found in 100 grams of propane. So we'll use that conversion factor to take the grams of propane that they give us. We'll multiply by the conversion factor, crossing out grams of propane, and we're left with 14.9 grams of hydrogen. Does the result make sense? The sum of these two masses equals 82 grams, which was the sample size, the grams that they gave us to begin with, to two significant figures, so we are good to go. The empirical formula of a compound then gives the lowest whole number ratio of atoms or moles of the elements in a compound, and an empirical formula may or may not be the same as the molecular formula. We'll go through some examples of this. The percent composition of a compound can be used to then calculate the empirical formula of that compound, and the percent composition will tell the ratio of masses of the elements in a compound. The ratio of masses can be changed to the ratio of moles by using conversion factors based on the molar mass of each element that you get from the periodic table, and the mole ratio is then reduced to the lowest whole number ratio to obtain the empirical formula of that compound. So we have a poem that we can follow the following steps always. Percent to mass, mass to mole, divide by small, multiply until whole. And we'll talk about what we mean by that. Doing percent to mass, mass to mole, divide by small, multiply by whole. And we'll talk about what I mean by that going through this next sample problem. So let's determine the empirical formula of a compound. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound? So let's take our first step in the poem, changing percent to mass. Assuming that you have a 100-gram sample and convert all your percentages to masses. So 25.9% nitrogen would be 25.9 grams of nitrogen, and 74.1% oxygen would be 74.1 grams of oxygen. So we're converting percent to mass. Then we're converting mass to mole. Convert the mass of each element into moles of each element by using the molar mass of that element. So we have 25.9 grams of nitrogen, and we'll multiply by the molar mass of each element that, again, you get from the periodic table. And we always know that that periodic table mass is equal to 1 mole of that atom. So 1 mole of nitrogen is equal to 14.01 grams of nitrogen. We cross off grams and we're left with 1.8486795,146 moles of nitrogen. And taking our 74.1 grams of oxygen, multiplying by 1 mole of oxygen per 16 grams of oxygen, we get 4.63125 moles of oxygen. And then divide by small, determine which of the mole amounts is the smallest, and then divide each mole amount by the smallest number of moles. So nitrogen had the smallest number of moles, and that will give us 1. And then we take oxygen and we divide it by the smallest number of moles. So does that make sense? We'll determine which of the mole amounts is the smallest, and then divide each mole amount by that smallest number of moles. So we'll get 1 for nitrogen, and we'll get 2.5051665058 for the oxygen ratio. Multiply unit until whole. So now determine what factor you need to multiply each mole amount by to get a whole number. Nitrogen, we have 1, and oxygen, we have 2.505. Nitrogen is already a whole number, so we leave it at 1. But for oxygen, if we multiply it by 2, we'll get a whole number. So that's the same number we multiply nitrogen by. So in this step, multiplying the unit whole, we determine what factor you need to multiply each mole amount by to get a whole number. And we know that needs to be 2, because when we multiply 2.5 times 2, we'll get 5. And we use that same number to multiply the nitrogen by. So that gives us our empirical formula, which will be N2O5, because we'll have 2 nitrogen and 5 oxygen. That one is a little trickier. Write the formula and place the whole number ratios as the subscripts for each element. Does the result make sense? The subscripts are whole numbers, and the percent composition of this empirical formula equals the percent given in the original problem. That one is a little trickier if you need to watch through those steps again. Then the molecular formula of a compound is either the same as its experimentally determined empirical formula, or it is a simple whole number multiple of its empirical formula. So once you have determined the empirical formula of a compound, you can determine its molecular formula if you know the compound's molar mass. So you can calculate the empirical formula mass of a compound from its empirical formula. This is simply the molar mass of the empirical formula, and then you divide the experimentally determined molar mass by the empirical formula mass. This quotient gives the number of empirical formula units in a molecule of the compound and is the multiplier then to convert the empirical formula to the molecular formula. Let's go through this in a sample problem, finding the molecular formula of a compound. Our question is calculate the molecular formula of a compound whose molar mass, this should be whose molar mass is 60 grams per mole, and the empirical formula is CH4N. We'll list the knowns and unknowns. We're going to divide the molar mass by the empirical formula mass to obtain a whole number, and then we'll multiply the empirical formula subscripts by this value to get the molecular formula. So we know the empirical formula is CH4N, and the molar mass is 60 grams per mole, and we're looking for the molecular formula for how many C's and how many H's and how many N's should be in that molecular formula. So first, calculate the empirical formula mass. So we'll take CH4N. We're going to take 12.01 grams per mole because we just have 1 carbon. We have 4 hydrogens at 1.008 grams per mole each, and then 1 nitrogen at 14.01 grams per mole. To get a total, the empirical formula mass is 30.052 grams per mole. Then we'll divide the molar mass by the empirical formula mass. So we'll take 60 grams per mole, the molar mass they give us, divide by the empirical formula mass 30 to get a whole number ratio 2. And then we can multiply the formula subscripts by this value. So instead of having 1 carbon times 2 would be 2 carbons, 4 hydrogens times 2 would be 8, and 1 nitrogen times 2 is 2. So that is our molecular formula. The result makes sense because the molecular formula has the same molar mass of the compound, and that is today's lesson. I know a lot in 10.3. If you guys have any questions, let me know. Good luck with all of your homework and assignments due this week and your test, and God's blessings.